Okay, we're going to be looking at chapter 22, as you can see, called Oxidation Reductions, also called redox reactions. So a brief overview is where oxidation reductions happen is really, these are some of the most important and principal sources of energy on Earth. Explosions, burning, redox reactions are known for being exceptionally exothermic, just kind of across the board. Now, the reason it's called oxidation reduction or redox is that oxidation reactions are always accompanied by a reduction, kind of like when we learned about Bronsted-Lowry acids and bases, that you really can't have an acid without a base. You can't have oxidation without reduction as well. So we talk about them at the same time. So what we're talking here, so kind of the overall view of this, and we're going to see a couple differences, but the overall view is that we're talking electrons being transferred. And this transfer of electrons between reactants is what we call an oxidation reduction reaction, or simply a redox reaction, like we see there. So where the oxygen comes from. So we talk oxidation reduction, and then I said it's all about electrons. So you might wonder, well, why is it called oxidation if it's about electrons? Well, the word oxidation originally meant to combine something with oxygen to give us something oxide. So you might hear people saying things like iron is oxidized. We call that rusting, forming iron oxide. You might hear about like fruit becoming oxidized, reacting with oxygen. So here's that rusting reaction. We can also oxidize compounds. So like we can oxidize methane, form carbon dioxide and water. Now, because of this, over time, reduction became the loss of oxygen, hence the word reduction. So oxidation reduction was always originally about oxygen, gaining or losing oxygen. So we can see here we have this iron oxide reacts with carbon to form iron, and carbon dioxide would be considered a reduction reaction. Now again, this is kind of the old school way of doing this. And things have changed over time. And again, these have to occur simultaneously. It turns out we cannot have oxidation without reduction as well. So like with the reaction we see here, as the Fe2O3 is reduced to iron, because it's turning into iron by losing oxygen, the carbon is oxidized because it's gaining the oxygen. That's where this terminology kind of came from, but we've evolved beyond. Now when we look at section 22.2, so now's where we're going to get into the electron transfer part of things. Now, again, we've extended this idea of oxidation reduction to not just be about the gaining or loss of oxygen, but to include all transfers or shifts or movement of electrons, which gives a much wider application. And it's really how we want to think about this is, what are the electrons doing? Are the electrons being gained or electrons being lost? So what we have to remember is oxidation is really in terms of this loss of electrons. This loss, oxidation is loss of electrons. We could view it as the gain of oxygen, but don't. So I would really just ignore that piece there. It's really about that loss of electrons. Likewise, reduction is the complete or partial gain of electrons or the loss of oxygen, but again, let's not focus on it in terms of oxygen. So it's really all about what's happening with electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. There's two mnemonics that I use to help remember this. The first and kind of the classical one is Leo the lion goes grr. So Leo, L-E-O, losing electrons is oxidation. Leo, grr, gaining electrons is reduction. That's kind of the classic one. You'll see that in a lot of textbooks. This one is the one I actually prefer. And in all honesty, every time I do these problems, this is what I break it down to. I just remember it's backwards. It's backwards from what I want it to be. So when I see the word reduction, I normally want to think, okay, reduction is loss, but no, it's backwards. So now reduction is gaining. And what are we gaining? We are gaining electrons. So if reduction is gaining electrons, that means oxidation is loss. Both work, you just have to remember it's some way. If you have another mnemonic that works for you, use your mnemonic. There's no right way to remember this, it just needs to be remembered. So let's look at this example here. This is a pretty straightforward example of redox. So we see we have solid elemental magnesium, solid elemental sulfur. We form magnesium sulfide, an ionic compound. Now in a metal-nonmetal reaction, magnesium being a metal, sulfur being a nonmetal, electrons are always going to be transferred from the metal to the nonmetal. This shouldn't surprise us. Metals form cations. Cations are positive, which means they lost electrons. Nonmetals form anions. Anions are negative, which means that they gained electrons. So for magnesium to form magnesium 2+, it has to lose 2 electrons. Sulfur to form sulfide with a 2 negative charge has to gain 2 electrons. So because magnesium lost 2 electrons and sulfur gained 2 electrons, I would say the sulfur was reduced. Again, I always go with the gain is reduction, which tells me that the magnesium was oxidized. So in an ionic compound, it's really easy to see what's going on with oxidation reduction. You can just look at what are the charges? What had to happen to those elements, to those atoms to make them the charge that they are? And so again, for a general rule, and if it's a metal and a nonmetal, so again, we're forming an ionic compound, the metal will be oxidized, the nonmetal is reduced, but again, break it down to what's happening. Now, just because your life is not complicated enough, you'll see the terminology of agents coming into play. So we're talking oxidizing agent or reducing agent. So whatever chemical donated the electrons is the reducing agent. So again, donating electrons is oxidation. So whoever is oxidized is also called the reducing agent. Likewise, whatever substance received electrons was reduced is the oxidizing agent. So whatever the thing is, oxidized or reduced, it's the other thing agent. Whoever is oxidized is the reducing agent. Whatever was reduced is the oxidizing agent. You'll see this terminology pop up now and then. It's a little annoying, but it is what it is. So another example. So this one's a little messier. So we see some silver nitrate plus copper metal, elemental copper. We're forming copper 3 nitrate. That's not an ion. Oh, anyways. And that should be a 2. That's much better. That 3 was bugging me. And 2 silvers. So we want to know who's being oxidized, who's being reduced. To do this, break it apart into its ions, very similar as if we were doing a net ionic equation. So I see the 2 silvers become 2 silvers, the 2 nitrates, copper to copper ions because it's a 2+ charge, and that there, and that there. So things that had charge that were in the compound still have charge. So now we look at this and I go, okay, like silver went from Ag plus to just Ag. I can also see that the copper went from just copper neutral to copper 2+. So the silver and the copper were involved in this redox. This nitrate though started as NO3 negative and is still NO3 negative. So it didn't really do anything. So again, that copper went from copper to copper 2+. To become copper 2+, it had to lose electrons. And what is loss of electrons? Oxidation. Likewise, the silver went from Ag plus to just Ag. To do that, it had to gain electrons, gain that negative charge to neutralize it out. Gaining electrons is reduction. So here, where we say the copper was oxidized, it can also be the reducing agent. Likewise, the silver that was reduced can also be considered oxidizing agent. And again, the nitrate did nothing. It was just there. That's okay. So ionic compounds and ionic reactions are pretty easy to see who's being oxidized, who's being reduced, because we can see a clear difference or change in charge. So again, just look at the compounds, look at their charges, look at the ions, makes it pretty apparent. Covalent compounds are harder though because they don't have a charge, but we can still do this. So if I look at like hydrogen and oxygen to form water. Now we're going to talk more about this in the next section, so don't panic overly much. So initially in this hydrogen-hydrogen bond, electrons are equally shared. It's nonpolar. In the oxygen-oxygen bond, electrons are equally shared. It's not polar. But in the oxygen-hydrogen-oxygen, so this water molecule, oxygen is going to pull the electrons towards it. So if you kind of remember, we'd see oxygen, hydrogen, hydrogen, and then there's this lone pair on the oxygen. The electrons are being pulled towards that oxygen. It's a polar molecule because of it. So the oxygen is partially gaining electrons, which still counts, making it being reduced. The hydrogens are partially losing the electrons, making them oxidized. So we can view it like that too. Now there is something coming up which will deal with that a little bit better, but just FYI. Now there's this chart. I would focus on really this kind of two pieces here, either loss of electrons or gain of electrons, or we're about to talk oxidation numbers. Don't worry about the rest. Focus on loss of electrons is oxidation. Gain of electrons is reduction. Again, I always remember gain of electrons is reduction because it's backwards. Reduction is gaining. And then we're going to talk about oxidation numbers in a moment. So now we're going to get into this thing called oxidation numbers. Oxidation numbers are a bookkeeping concept. They're a way to consistently look at are things being oxidized or reduced. Again, they're a bookkeeping number, and what an oxidation number is, it is a positive or negative number, a value, assigned to an atom according to a set of arbitrary rules. The idea behind oxidation numbers is that if this compound were ionic, if these atoms were ionic, what would their charge be? Not that they are, but if they were, what would their charge be? So we're going to walk through these rules that you need to know to find oxidation numbers. And we can actually balance complex reactions using oxidation numbers alone, which we're not going to do. So there's 5 rules that we're dealing with. First, the oxidation number of a monatomic ion is whatever its charge is. So if we see an ion and it has a charge, that's its oxidation number. So if I have this compound here, calcium bromide, the calcium is a 2+ charge. The bromide has a -1 because that's its charge. So then the calcium ion has an oxidation number of 2+, while the bromide ion has an oxidation number of 1-. If it's charged, that's its oxidation number. 2, hydrogen will be +1 unless it's bonded to a metal, then it'll be -1. It's just what it is. So like in water, H2O, each of the 2 hydrogens has an oxidation number of +1 because it's bonded to a nonmetal. Oxygen will always have a 2- in a compound. Oxidation in a compound is -2, except if it's a peroxide ion, it's -1. We're not going to deal with that this year, so don't worry about that. So like in oxygen, the oxygen has an oxidation number of 2- because that's oxygen being there, whereas in peroxide, it would be a 1-. The oxidation number of an element, pure element, not in a compound. The oxidation of a pure element will be 0. Doesn't matter what the element is, we're just saying if it's a pure element, it's 0. If it's potassium metal, it's 0. If it's oxygen gas, it's 0. In its elemental form, oxidation numbers will always be 0. Finally, for any compound, the oxidation numbers of each atom needs to add up to the charge on the compound. And that's really where we're going to see things coming in. So what we're going to do now is we're going to look at a few different compounds and figure out the oxidation number of each atom there. So I'm going to start with this S2O3. Okay. There's no ions present. It's not pure element, so first few rules go away. Oxygen will always be a 2 negative because that's what oxygen is in a compound. There's 3 of them, so there's a total of 6 negatives. Now, the overall compound we see here is neutral. So that means if there's 6 negative charges, there also has to be 6 positive charges because the compound's neutral. The oxidation numbers have to add up. So then we can say, so what does sulfur have to be in order for 2 of them to equal 6 plus, and that would be a 3 plus. So in this case, the sulfur would have an oxidation number of 3 plus. The oxygen would have an oxidation number of 2 negative. Okay, let's look at oxygen, O2. Well, that's an element. Pure element, so therefore its oxidation number is 0. Let's look at this aluminum sulfate. Now it's almost easier to view this as aluminum and as sulfate. Now this aluminum here is in a compound. Because it's in a compound and it's a metal, it has a charge. It's ionic. What charge does aluminum have? Aluminum always has a 3 plus charge. Therefore, this aluminum has an oxidation number of 3 plus. Now the sulfate's a little tougher. So again, we can go with each oxygen is a 2 negative. There's 4 of them, so that means there's a total of 8 negatives. Now the overall charge on a sulfate is 2 negatives. So we ask ourselves, what plus 8 negative is 2 negative? And the answer is plus 6. There's only 1 sulfur, so the oxidation number on that sulfur is 6. So again, we're going through the atoms item by item. Now this last one, little sneaky. I would not ask this on a quiz. So we see sodium, and now we get this peroxide ion. Because sodium has a +1 charge, it has an oxidation number of 1 plus. Now oxygen is normally a 2 negative, but in this peroxide case, it's a 1 negative. Sorry, 2 negative charge there. Yeah, I think in my mind, the first 3 perfectly fair questions to see on a quiz. The last one, probably not. So now let's look at the oxidation number of just phosphorus in each of these following substances. So we'll do these one by one. Now we really have to figure out everything, but I'm really focused on the phosphorus. So the P4O8. Okay, oxygen is a 2 negative. There's 8 of them, so that means there's 16 negatives. The overall compound is neutral, so that means there's 16 positives. And then, so what does the oxidation number on the phosphorus have to be for 4 of them to equal 16? And the answer is +4. So this one has an oxidation number of the phosphorus of +4. Now for phosphate, PO4 3 negative. Once again, oxygen is a 2 negative. 2 negative times 4 is 8 negative. So what plus 8 negative equals 3 negative? And the answer is +5. There's only 1 phosphorus, so it has an oxidation number of +5. Third one, P2O5. Again, oxygen, 2 negative. Gives us 10 negative total. There's no charge on the compound. So if there's 10 negative, that means there has to be 10 positive. And if there's 2 phosphoruses for a total of 10 plus, each phosphorus has to be +5. Number 4, P4O6. There we go. Again, each oxygen is a 2 negative. There's 6 of them, so that means 12 negative total. Overall compound is neutral, so 12 positive. There's 4 phosphoruses, total of 12 plus, so each phosphorus has to be plus 3. Now H2PO4 is a little sneakier. Again, I can say, okay, oxygen is a 2 negative, gives us 8 negative total. Now there's hydrogens here. Now remember, hydrogen will be plus 1 unless it's attached to metals, which it's not. These are all nonmetals. So each hydrogen is a plus 1, which gives us a plus 2. So if the compound has an overall charge of a single negative, like we see right there, we have a plus 2 and a negative 8. What does that phosphorus have to be? So if I look at just the plus 2 and the negative 8, that adds up to negative 6. So in other words, what plus negative 6 equals negative 1? And that is plus 5. And finally, PO3 to 3 negative charge, phosphite. H oxygen, once again, is a 2 negative. There's 3 of them, so 6 negative. Overall compound has a charge of 3 negative, so that means that the phosphorus has to be providing a 3 plus. There's only 1 phosphorus, so plus 3. Notice I'm having to go through this item by item, atom by atom, piece by piece. It's what is necessary. You cannot do this any other way. There's no shortcuts, no workarounds. It's what it requires. Anyway, that's it. Good luck.